I think it's time to open this, I think, very special event, the first National Science Foundation workshop for outstanding teachers and outstanding researchers. I think we witness something that is extraordinary, and I'm particularly excited about this workshop. So I'm honored to open this workshop and welcome outstanding teachers. I use outstanding because I have to justify how selection was done. It was initially, we contacted magnet schools of mathematics and science. It didn't work very well. Probably you know very well that if I send to your principal, maybe only Principal Steve Warshaw passes to other teachers, but probably somewhere information is stuck. But when we later on, we put in presidential awardees list, we were very successful. So all of you, first of all, congratulations to most of you who are outstanding teachers, and you can find your names on the list. Other people, some other people, how they found the place here, because they were strongly recommended by my dear colleagues, control people. When I asked, please identify a teacher in your area, that was a wonderful, wonderful experience. They were looking for those the best. So you are the best, and welcome here. And also, I am extremely grateful to speakers who took time and prepared outstanding lectures for you, and they prepared long lectures for you, and then I had to hurt them by shortening the lectures, because NSF education program cared so much about you, teachers, that you are supposed to have voice here. You are supposed to discuss. You are supposed to talk, not long talks by speakers. And I know, and maybe Professor Pasik-Duncan knows how I felt when I had to tell those people, you have to shorten your talks. So I believe that we are flexible, and if those outstanding speakers want to speak longer, just please do it. Now NSF accepted program, so we can slightly change and just simply do what we like the most. And obviously I'm very grateful already for teachers' feedback. As you look at web page, teachers already gave me input. They said what the expectations are. I was so pleased to read how excited they are about control and systems theory, because this is what I'm doing for living, and this is what I love to do, and we love to do. We really believe in control. We know that you cannot exist without control. You know, and you are not aware that control is everywhere around us. Even when you have to put your money either in stock or in safe asset, you have to control optimally. So whatever you do, you need to control. And you will hear today about control. The reason why we talk about control, the reason why my heart goes to control, and I am by all education, I am a mathematician, but I found home among engineers, and in this particular society, control system society. Why? Because this area motivates me so beautifully for teaching my students, for showing them applications, for motivating them for studying mathematics. And you will hear today, and this is what's supposed to be, what this workshop is supposed to be. We won't teach you because you are outstanding. We cannot teach you. You know how to teach. You will probably teach us how to teach. But what we want to show you, we want to show you the beauty of control, our systems, filtering, all kinds of things. But I also brought other people when at certain moment as mathematician, when I read Newsweek and I look at difficult formula, math equals fun. And this is what we do at KU, University of Kansas. We show people that math is fun, nothing difficult. And then I called this man and I said to now is very famous because he was in Newsweek. The picture of him was in Newsweek. So I called him and I said, can you do something for me? Can you make this workshop successful and come? And he's among us. He came. He says, sure, I can do this for you. So, you know, and all other people did a lot for me. This workshop is successful because all people, Control System Society and American Control, you know, Council, right? Do I say correctly? Control Council? No, how should I say that? You know, so all of them assisted me, but most importantly, I was just a single person without any kind of administrative help, and I got from Professor Ulsoy this outstanding help of Randy Freeman, who assisted me with everything, whatever I requested or whatever I didn't request, but he figured out that I should have requested. And we have today, I believe everything what we need. And we obviously, a stochastic person, I believe in disturbance. I believe that some disturbance will still occur. Some people even think if you are stochastic, all rare events are around. Dr. Kishan Baheti, who sponsors this workshop, he called me 5:30 in the morning that his flight was canceled, but he is on the way. So at any moment he will come. So, you know, he will join us a little bit later, but at this moment I would like to say thank you to Program Committee. You have all these people listed. If you can stand those on Program Committee, Molly, Tyrone, Chris, and all others who are on the Program Committee, thank you for your assistance, for help, and to put together this program. And to all speakers, to all of you, and now I would like to introduce our President of Control System Society. I am proud of being part of this society, Professor Tamer Basar, President of Control System Society.
Thank you, Bozenna. I'm very pleased to see you all here and also to be here. I would like to welcome you all to this unique event. I see this as a historic event in the history of Control System Society as well as the American Control Council. As Bozenna indicated, I'm the current president of the Control System Society, which is a society of IEEE, and that you can follow, other examples that you can follow. And Professor Pasik-Duncan has done an outstanding job, and it was a very challenging job to initiate all this and to bring this all together. And I see in the program that many high schools from different parts of the country are represented here. And I wish you all a very rewarding day. And I'm sure you will take back to the classroom the experiences that you have gained here, and at least know where to contact in case you have questions on control theory and how it impacts our lives. Thank you and welcome.
Another president, this time president of American Automatic Control Council, Professor Naim Kheir.
Good morning to all of you, and it's kind of difficult to sit in this room while the sun is out and it's 72 degrees outside. It's with great pleasure that I welcome you as the current president of the American Control Council. Probably have no idea what the American Control Council is. It's a group of societies, technical societies, including the IEEE, where Professor Basar is the president, and the American Society for Mechanical Engineers, Aerospace Engineers. All of these together made the council, and we oversee the operations of the control conference that will start tomorrow. So we're very delighted to welcome you here in Chicago and to this exciting workshop. I really congratulate you on being selected to participate, and I also commend the National Science Foundation, especially Dr. Baheti, who is not here yet, and for its continued efforts and commitment in support of control systems, their applications, technology, and education in general. special congratulations goes to Bozenna, of course, for her magnificent efforts and cooperating to make it a success. Now, those of us who are in higher education are always interested in ways to excite high school students in new areas. And we all have witnessed the excitement resulting from the internet and the extensive use of computers in high schools these days. However, in my opinion, the scope of this workshop and the very interesting presentations by such an outstanding group of speakers addressing real-world applications, these applications are very essential in general in creating awareness among your high school students. This awareness, I expect, will attract a new wave of students and perhaps new scholars in the near future who might not have otherwise been interested in studying engineering or studying control systems. The interesting thing about automatic control, as Professor Bozenna mentioned earlier, is that each one of us participated, whether we know it or not. Sometimes, for example, when you try to put your hand, I move my hand here to locate this device here, already my mind recognizes where it is, and then it sends signals to my hand to locate this. It appears to be a very trivial example, we do it automatically, but this is really a control problem. Another application that we use every day when we try to, without too heavy drinking now, trying to drive, locating our car in the middle of the lane. We observe where we should be, and take action with our hands to locate our car in the right position. We all have automatic heating and cooling in our homes. These are also control applications in our cars, etc. However, the most impressive and most sophisticated applications are, say, in flight controls, in transportation systems, even the auto industry being coming from the Detroit area. We are very heavy in the auto industry. Examples like collision avoidance system. That's a pure control application which might benefit us as drivers in terms of safety. Now, this workshop, I hope, will be a great eye-opener to your high school students. So enjoy this workshop and enjoy Chicago. Before I conclude, I added a couple of notes here that I would like to share with you. Being in higher education for more than 30 years, I have participated in many math clubs, physics clubs in high schools, and being invited to come and sit on the stage maybe for 15-20 minutes during the lunch hour rather than taking special time. And believe me, if you try where you are to connect with some engineering faculty in your community, invite them to speak for 15-20 minutes and answer questions to your students about engineering education, it will be very, very beneficial, especially having the material that you will get from here. Let me conclude by inviting you also, if you have time tonight or tomorrow, to visit the exhibits hall in conjunction with the American Control Conference, which would be in this area, I believe, outside. Exhibitors from all over the world come, and they have hardware and demonstrations and brochures and flyers, and I think this will benefit you to collect some of them. Enjoy your day. Thank you.
And this time I will ask Professor Galip, General Chair of this conference, Automatic Control Conference, that as the American Control Conference that accommodated us so beautifully and allow us to be associated with.
Thank you, Bozenna. The American Control Conference starts tomorrow, and even though it's called the American Control Conference, there will be people from all over the world, control engineers, probably over 1,000 people coming here, and we'll have over 900 technical presentations coming up in the next few days. There's also, as Naim mentioned, a nice exhibits area, and the conference registration desk in the exhibits area is one floor down at the Regency desk, and I would invite you to come down there if there's anything we can do to help. Bozenna mentioned that I'm the general chair of the conference, and what that means is that I'm one of about 10 or so volunteers that make up the operating committee from different societies, mechanical engineering, electrical engineering, chemical, and so on. And one of the reasons that we take time away from our families and try to organize this conference is we really enjoy control engineering. And you're probably wondering why, but I hope by the end of the day you'll understand the reasons for some of our passion, and you'll communicate some of that to your students. And if you do, I think we'll have had a very successful workshop. I want to thank NSF and Bozenna for organizing this, and I hope that you have a wonderful event. If there's anything that we can do as your host here to help, please come downstairs to the registration desk and we'll try to help out.
Hello, good morning. On behalf of the National Science Foundation, I'd like to welcome all of you. And really, this is one of the first workshop, not only in the Control Society history, but the history of NSF, where I think we are really going actively, not only saying about research and education, but really trying to do something about it. So in that case, I think it's really a historic event. Even our director of NSF know about this workshop, and she sends her greetings to you.
It's certainly an honor to have been asked by Bozenna to give a talk and to be the first speaker. And what I tried to do was choose a topic that I'm really personally interested in. And I think it made sense to start out with some background. So I'm going to do everything about year 0 to this century to sort of tell you where things came from. And I think make one of the most fundamental and critical ideas in the field, namely feedback, a little more concrete. Feedback is an idea, and the idea is that in its most basic form, there are two systems, and these systems, System 1 and System 2, will interact. In other words, System 1 will have some influence on System 2, and System 2 will have some influence on System 1. Well, the big advance that occurred in 1377 was this device, which I remember seeing this once in a museum when I was, I don't know, maybe in elementary school, and I was absolutely fascinated by it. You have to sort of stand and watch this thing, and I'm sorry I don't have the videotape of one working. But what this is the oldest escapement known. It's a mechanical device, and what you have here is a shaft, and connected to the shaft is a gear with teeth. It's called the crown gear. And if the crown gear was the only object here, it would just keep on spinning and perhaps accelerate, because as you see, there'd be a mass attached to this. But what keeps the crown gear spinning is this device, which is basically a shaft here with 2 paddle wheels and some weights up here. And what happens is this upper paddle wheel will engage a tooth, then the crown gear will push the paddle, and then the lower paddle will engage another tooth. And this goes back and forth. So instead of the crown gear just spinning freely, it'll basically speed up, slow down, speed up, slow down, and basically you have what's called an escapement that will regulate speed in the clock. Well, anyway, as we move the story forward, this fellow, John Harrison, a brilliant watchmaker in England in the 18th century, he invented yet another escapement. This is a very delicate, intricate, and precise escapement called the grasshopper escapement. And this is basically a picture of that. And he used that escapement to build this clock, which weighed approximately 80 pounds, had 2 escapements. The trick was not just to build a precise clock, but a precise clock that could survive an ocean voyage where it would be very hot and very cold, changes in humidity, and the rolling of the ship too. Well, after another couple decades of work, he produced this essentially pocket watch, which is thought to be the Mona Lisa of all watches. It was accurate to 1/3 of a second per day, and when tested on this voyage to the New World, was able to essentially locate the island of Barbados within less than 10 miles. And finally, for my last slide, all I'd like to say is that there are many manifestations of feedback throughout society and biology, and I'm sure the other speakers will talk about that. But there's one feedback loop that I think is the most important of all, that no matter what technological developments occur, we'll never get away from it, and that's the feedback loop that occurs between learning and teaching, especially when the teacher becomes the learner and the learner becomes the teacher. And I'm sure you know this quite well, and I think I'll stop right there. Thank you very much.
Thank you very much. Before we get into this session, I just want to thank Bozenna for putting this workshop together. I don't know how many of you know this, but Bozenna has always been a great supporter of mathematicians and engineers from underrepresented countries, young mathematicians and engineers, and women in control. And now she's also supporting high school teachers. So she's got her hand in everything, and I want to thank her for that. Actually, our first talk by Dennis Bernstein was the first talk of this session. We changed the order around
terms that pop up: control, system, and automation. What we want to do when we talk about automatic control is take something that we call a system, control it, and as Dennis very eloquently described to us, we'd like to do it automatically. And let me go to the more intelligent control. Now this is a real flush toilet. Here it is. Okay, this is the system, in yellow. This is the toilet tank, and this is where water will be coming in from. This is the controller, and this is where it's coming out of. And this is you producing flushing commands. So every once in a while in this little simulator, what I've done is I have an on-off source. So basically you flushing at will, and I've even put some randomness in there so the flushing command comes at random points in time. And whenever flushing occurs, you'll see this water level go way down. You're empty the tank, but immediately there is a sensing mechanism in the controller that realizes that you're flushing. So basically that floater device is now loose, and you're trying to fill in with water again. And you see this little red ball here? When it's at this position, it means that the valve is closed, and when it moves to this position, it means that the valve is open. So when a flushing command is issued, if the controller works properly, this little ball will move over there, open the valve, and then let the water rise to the desired level, and then stop, just right. But now I have feedback, because what this is doing here, it's essentially the flotation device sensing the level of the tank and telling the controller to shut off as soon as the proper level is reached. So let me start this very simple simulation. There it is. It's filling up. See, you saw this thing moving. So time, by the way, goes by here. And so we're waiting for the next flush. There it goes, boom, down, and immediately you fill up again. And notice when the level is reached, boom, automatically, this is automation, automatically the controller shuts off the valve that lets water in. And there we go again, another flush, and filling up again, and so on and so forth. And I think this is just a simple demonstration of how you can, it took me about 15 minutes to put this together, but most of the time was taken by writing this text, not actually even constructing the model. So once you get to know these little tools, and again, all these tools exist in the library, you can pull them together and you can build all sorts of fun things for the students, and even more exciting is to let the students do it. So I just wanted to show you that besides all these ideas and concepts, we also have some tools that we can get to you, or you can get for yourselves, and have fun with them. You can really just simulate just about anything you can imagine in the world with this simple software. Thank you.
Are there any questions? This is a question kind of to the audience as well. I'm from Lawrence, Kansas, and you said you were worried about, you know, the level of expertise of whoever's going to build your next car or whatever. 15 years ago, we were teaching computer programming in our school, basic computer programming, a little bit of Fortran. We're not teaching that anymore. What are other districts doing? Do they have computer programming in the high school anymore?
No, they don't.
It's growing?
We're teaching Cisco systems repair, stuff for vocational work out there.
But I think that's a concern that as educators we need to look at and address, because I don't think there's a universal push out there in that direction. Yes.
On a similar wavelength, what you're showing is sort of pre-engineering. In some ways, this conference, what I've heard this morning, indicates more, instead of National Science Foundation, it's the National Engineering and Technology Foundation. And in schools, you wonder whether, if you're teaching pre-engineering concepts such as this, whether you're really teaching what you should be in science, or whether this is a transient situation, such as the programming that will suddenly no longer be needed. That we need a lot of engineers, we heard in the early 80s, and then suddenly they didn't. I'm wondering whether you see this as a critical aspect of
I think you're making a very good point, and it goes back to the previous point as well. Okay, if we don't get the job right, things can get really messed up. What I'm trying to convey here is that we're building such incredibly complex and vicious systems that if we don't do it right, it could be catastrophic. Okay, so again, I don't mean to be paranoid here, but there is this urgency that we feel. And you're absolutely right. The most important thing is just play. It doesn't matter whether it's Legos or whether it's airplanes or whatever it is. Just play with something and exercise your judgment and your creativity.
I briefly introduce Brian Rosen, that is Senior Technical Director at Kheir Animation Studio, and he's going to talk about controlling the fictional world, making digital feature film. So here is our story.
That is correct. I'm Brian Rosen. I come here all the way from sunny California. Work at Kheir Animation Studios. We are the people responsible for making Toy Story, Bugs Life, Toy Story 2, along with our partners, Walt Disney, we will hear Alan Kay from later on this afternoon, I believe. The goal of this talk is to give you something of a background about how computer graphics actually works. In computer graphics, we have this wonderful thing which is easy to, really visible, really tangible, really easy to get excited about, yet its complete basis is completely mathematical. Everything about it exists purely because we understand the math under it, and we can generate these images completely through mathematics. So let's start by giving you an overview of the process that we go through when we're making these movies. So it turns out that a very useful thing is the idea of parametric curves, where rather than y being a function of x, we have some parameter called t, or we'll call it t. So in 2 dimensions, we basically just parameterize it. And here, this is a pretty simple concept that most of you are pretty familiar with, and it's a great way of just introducing it to your students. If you're trying to explain parametric curves, say, well, this is actually how Woody in Toy Story was made. So the question is, and actually in our world, we actually have a z of t as well, since we are in 3 dimensions. The question is, well, what is this f of t? What functions are we going to use? Well, it's actually kind of wide open to us. We could use anything we wanted. It turns out that what works very well for computer graphics is using cubics, so a cubic polynomial. It so happens that in the auto mechanics world, they use 4th degree. They use 4th degree polynomials to get at their stuff. The reason they do that is because there are various aerodynamic equations which kind of fall out of their use of these higher degrees. For us, we're very happy with cubics. So here we have a curve. If we specify the starting point, that would be P1, then the ending point, which would be P2, and then the direction of the curve, which is R1 at the starting point, then the direction of the curve at the ending, well, we have 12 values right here. This should completely constrain the problem. There should be one, and only one cubic that has these properties. But through pretty simple substitution, since you have 4 constraints, you know that at t0, this should be P1. At t equals 1, this should be equal to P2. And then if you take the derivative at P0, it should equal this. And the derivative at T1 should equal this. One curve, another curve, another curve. And we end up with a mesh where we take the columns of these points and they define curves in the other direction. And by doing this, we end up generating spline meshes. And again, now we have a web of control points where we can take all these control points which we can take here, grab and move interactively and change the underlying surface. So that's how computer graphics, the actual geometry of computer graphics is specified through
control using pendulum. Pendulum is something like this. You know, when I started to learn about the pendulum, that's about the early, I think, be that the student, didn't understand so much about the control, because the control theory is so the mathematics and so on. So the student said it's not so much interesting. So I started to ask them to study about the pendulum and how to control pendulum. Yeah. So this is kind of the pendulum movement. This part there is the no control, but there is arms connected to this pendulum. The nice thing is if you properly move this one, you can swing up the pendulum from the bottom to the top. It's something like this. So this is one of the the control which that makes this pendulum position to the upright position. So this is the pendulum like this. Yeah, but this is just straight. So, but you keep the pendulum, and this is the pendulum like this. This part there is the arm. So by properly controlling the pendulum, the double pendulum can be stabilized. There is no string force. So this pendulum and there's another pendulum and just keep. So the double pendulum can be stabilized. This kind of things is shown is possible to be stabilized by just the analyzing characteristic of the system. When they said controllable, it's possible to be stabilized. So this is one of the the things which we can use, control and so on.
I wanted to implement, I wanted to say something that I haven't said. We are planning, as I told you many times today, this is the beginning. So we are planning, look over there is the beginning of video or whatever, videotaping. And my university was generous and promised that we should make like video from all here. And also I communicated with speakers, asking them very kindly to prepare some stuff later on that we will put on our web page. And so you will have, I'm pretty sure, a lot to share with you, with others at your schools, and you're supposed to stand as ambassadors, and to this program, outreach program.
Giving you a little better appreciation about automatic control. Okay, well, the specific control problem that I chose is collision avoidance. We don't have such systems operating in cars out there, commercially available, even though folks out in California, a bunch of schools and industries have been developing prototype such systems. They're not commercially available. So let's look at this very simple application. All of us can do this, not with eyes closed. Say I'm standing right in front of this wall, and what I would like to do is move in a straight line and stop 3 feet away from the wall. Go ahead, do it. Is it 3 feet? Well, my perception of 3 feet and so on and so forth. But what did I actually do here? Manually, I was able to control my body to do this. Well, suppose that we would like a vehicle to do this exact same operation. So we're going to try and do this with this little toy car that we put together. A couple of my graduate students designed it and built it a few years ago. And we're using it now for demonstration purposes. But it's going to serve the purposes of what I'm trying to get across. Here is the little car. It's battery operated. It has a servo motor in the back. For a gear system, the wheels turn. And basically, let's see how we're going to go about solving this problem as it applies to this hand.
You loaded that microprocessor?
No, the microprocessor is already there. All I did is I just changed the parameter, and I downloaded it in there. So, and that parameter is going to be used in the control strategy. There we go. So, the idea here is the following. Theory, simulations, experiments, all work together in order to solve problems. What you just saw is some activity that we've had at the University of Massachusetts over the last 4 or 5 years in trying to take control concepts which usually are reserved for high-level undergraduates and graduate students and bring them to first-year students. So what I'm going to talk about is a rather large project that's been going on at Cornell University, and the mission is to bring together a whole bunch of students from very different disciplines, mechanical engineering, computer science, electrical engineering, put them in a project environment where they can use the skills that they've acquired throughout their undergraduate experience to build something complex. And this is a great educational experience. There's a lot of interesting research aspects associated with it, but I'm going to stress the educational aspects today. And I think something like this can be done starting at the high school level, clearly in a different scope than this. But there is the hardware available where you can do a lot of this stuff at the high school level, and a lot of it is with Legos, as people already talked about today, as Chris was mentioned. So let me talk a little about this RoboCup, this robot soccer. Before I get into some of the details of the project, I thought the best thing to do is just to give you a 1-minute clip to give you an idea of what robot soccer is. Keep in mind that when you see this, when you see these little machines move around, there is nobody controlling them. There's nobody with a joystick that's moving them around. They're making decisions on their own and acting on their environment. This part here, when it's a little frustrated, starts kicking the defender instead. Okay, so this is, yeah, exactly. That's what RoboCup is. Actually, that's the name of the guy that brought the little routine to go around obstacles. Yeah, they're trying to sequence their plays so they can. You got it.
referred to in this graph.
And we're doing analysis actually in real time on up to 128 channels. But with 16 of them, you have one of these outputs on every channel, and you can put it together to get a composite, or you can look at it individually on each channel. This is like a topographic map looking down on a mountain, trying to figure out what they call level curves. How high is the intensity of seizure at each place in the right temporal lobe and left temporal lobe, and you can see that a seizure sort of starts here at this location, dies out, comes back. This is when the patient's aware. And if on the very next day, we detected another seizure for the same patient, and if you look at a graph of what that looks like, in terms of the fingerprint and pattern of where seizures start, how they spread, and how long they last, this looks very similar. It's the little graphical display of this here. This is that same signal with the feedback gain of 0, and if you click on this slider, it's going to increase the feedback or make it go from 0 down to -1. And as I do this, you can see the seizure basically disappears as you subtract the seizure component from the non-seizure component. This leads to questions about stabilization and so on. Another problem, one potential problem that you have to be careful of with feedback systems is if you feed them back out of phase, or if your gain is wrong, if your gain went positive, you can actually make matters worse by feeding the seizure back to add to this and just double the intensity. You can get lack of stability.
Here we have a patient, and this is a demonstration of the algorithm in real time. This lady has probes inside the brain. She's in a special unit that we have for these studies. The person is sleeping. We superimpose the computer screen. This is the raw signal, and underneath is the output, is the transformed signal, the ratio. As you can see, the threshold, as evident by the dotted line, was crossed at what was the time, Max?
8:12:50 or so. This is cross threshold. You can see the signal looks relatively similar to what it did in background. And the patient's just resting, unaware that the seizure's coming in. She's been instructed to push a button if she feels the seizure come on, or call out for the nurses. And this is a relatively gradual onset of seizure.
The ratio, the seizure content will increase. The trend obviously will be towards increase, will reach a peak sometime later. You can see that it will saturate at some point and stay there with this long. The patient remains asleep and completely unaware. The patient moves now, but these movements are normal, as you can see. Very different from the seizure movements. You can hear how she says help me now. She felt the seizure. No evidence of seizure. At this point, you see the head begins jerking towards the left. This is the beginning of the seizure, and the seizure will spread to involve the entire brain, and will be transformed into a convulsion. In this particular case, I think we were able to predict the seizure with about 1 minute and 30 seconds approximately. The ratio tracks the signal, the raw signal, point by point, and you'll see that as the seizure begins to wind down.
At this point, is it too late to do anything with electrical stimulation?
Well, it depends on from where you intervene. If you intervene from centers that connect, to everywhere in the brain, then it may not. But you don't want to get to this point. You how now the seizure is dying down and we see now the ratio decrease. Are there any questions there? Right. Thank you.
I really wanted to make a presentation at this meeting, so I thought it might be a good idea if I captured a talk that I gave just a few days before we went off to Europe to the National Academy of Sciences. It's on exactly the same topic as I was going to talk about at this meeting, and after the talk I will be available by teleconference for questions. So thanks a lot, and here we go. Do gravity experiments, and the way we do science is by actual reference to the real world. I don't believe you can learn science from a book, because you can write lies in a book. I don't believe you can learn science on a computer, because a computer can simulate an inverse cube law just as easily as it can simulate an inverse square law. So you're always basically put in the position of having to believe somebody in mathematics. Einstein had this nice saying. He said you have to be able to learn how to distinguish between what is true and what is real. And what he meant is that what is true is what you can put in language in mathematics. That's because the truth comes from its non-contradiction stuff, but what is true is not necessarily what is real. What is real is the way the universe wants to be, and they're really two different things. And so we do it by actual references to the physical world, like somebody dropping a water balloon, and then having the kid measure using this little measure. So for instance, if you measure from the middle of the balloon to the middle of the next balloon, this is every 10 frames here, they quickly see that they have to increase this measure by some amount each time. And then by stacking these guys up, they say, oh yeah, the amount that's getting increased is just about constant. And that leads them to this two-stage increase by, which gives you gravity. In the music world, the two-stage increase by gives you FM synthesis, which is the synthesis that's used by the Yamaha synthesizer. So the belief here, and this is justified by quite a bit of experience, that simply putting kids into a play world that has powerful things, powerful ideas that are used over and over again in different contexts, that these become part of the kids' heuristic thinking. And I believe that if we're ever going to have more than a few percentage of the population really understand science, that's what we have to do. We have to change kids' common sense into uncommon sense. Thank you.
This is going to be something different. A lot of other people have been giving you some very good ideas about things you can bring into the classroom, work with students. What I want to talk about is the style of presentation that people have in the classroom. And I teach mathematics at Williams College. I've been teaching there for 15 years now. And what I've found, and I think you as teachers of mathematics already know this, that there are two basic goals when you teach mathematics. Number one is to get across this body of material, whatever the body of material is, whether it's trigonometry, calculus, algebra, whatever it is, you want to get that material across. But I think that's secondary to the real goal that you have when you're teaching a group of students mathematics, and that's to excite them about the material. But, so let me give you an example of a prop that I use in calculus, and this is when I'm talking about the limit. Okay, and the idea of the limit, which is a very hard idea to get across to students, is this idea of something getting closer and closer to something else. You don't care what happens at the value you're approaching, you only care what happens as you approach that value. And the way I demonstrate that is with a fan and a pinwheel. Okay? So I'm going to have the fan here, and I'm going to actually, you got to do this sort of carefully, I'm going to take the cover off the fan. And some of you in the back, you might want to stand up to see this because it's on the table, you might not be able to see it very well. But so I'm taking the cover off the fan so you can really see it, and I'm going to turn the fan on. It's really going, okay? And I'm going to look at what happens, the limit of the rate of spin of the pinwheel as the pinwheel approaches the fan, which I'm just assuming is at a 0.7. And you can see sort of the rate of spin in revolutions per second. It starts at 3 when I'm 5, when I'm at coordinate 5, and as I approach coordinate 7, I'm getting closer and closer to that. And then you can actually take the wheel and you start approaching, and in the beginning, of course, it's not doing much, and then it starts to spin, and it spins faster. You know, the thing is, though, you have to be very careful in this, because when the thing opens, oh my gosh! I've got ketchup all over my head. Okay, it's a very stupid little trick, but students like it. I did it once at a conference, and the poor woman who was organizing it jumped up and ran out of the room to get help, and I go, okay. Let's see, another one I wanted to mention in terms of gags was something that I did when I was on leave at the University of California, Santa Barbara, and I was teaching there. You are teaching these very large lectures, and I was going to teach a really large lecture of calculus, and I was a visiting professor, so none of the students knew me at all. And so the first day of class, I went in and I sat down in the front of the room. And the auditorium is, filling up with students. And these two women are sitting on either side of me, and the one leans over me to say, "What have you heard about the professor?" And the other one says, "Well, I'm hoping this will be interesting." And she says, "Well, he's a visitor. I haven't heard anything about him." Okay, too bad. And then I had my colleague come in, Daryl Cooper, who teaches at the University of California, Santa Barbara, and he comes up to the front of the room and he says, "Hello, I'm Colin Adams, and I'll be teaching this course. And I have lots of things to tell you about how the course will be run, but I think I'm going to start right off with some review, and we're going to do some review of inequalities. And we're going to start with the inequality x minus 7 quantity over x plus 3 is less than 2. And the first thing we're going to do is we're going to multiply through by this denominator x plus 2, and he multiplies through by the denominator. And at that point, I sort of timidly raise my hand. There's 150 students behind me, and I sort of timidly raise my hand, and they're assuming I'm a student. I say, "Excuse me, professor, but isn't it true that if the x plus 2 is negative, you have to change the direction on the inequality?" And Daryl just freezes, and he goes, "Well, if you're so darn smart, you teach the class," and he throws the chalkboard and he storms out of the room. There's like 150 just stunned students, their mouths open, they're like, "Oh my gosh." And I sort of looked around and I sort of, well, okay, I guess I'm like I'm crazy, like I'm completely insane. And I get up to the front of the room and I said, "I guess I'll just finish the inequality," and I sort of keep working on the inequality, I'm working it out. And slowly, in this 150 people there, slowly you see sort of a smile here and a smile there, and a lot of still open mouths, Well, he left these syllabi on the table, I guess I'll just pass them out, and I start passing out the syllabi. And by the end of the class, I would say that 95% of the students knew what had happened, had figured it out, and there were still 5% who didn't.
But at the beginning, our past president of Control Systems Society.
I just want to take this opportunity to say that this has been a very stimulating experience for me, and I was involved and supportive of the organization of this program, like thanks to the National Science Foundation. This is really the first opportunity to have this kind of an event at one of the regular control conferences, and we certainly look forward to getting feedback from you about your thoughts about the day, and of course that's one of the things you need to digest a little bit, but I think it is an opportunity for this particular group to express itself and to interact with people who are at the front lines of providing math and science opportunities for students at all levels and preparing them for their future Automatic Control Council. Anyway, Professor, come and sit down.
I just got here, and I missed the whole exciting part that I'm sure you had a wonderful day about talking about controls. When this idea was first brought to us, we are quite excited and immediately wanted to be a part of this. I think the high school education is probably the most important part for us. The engineering school, I'm coming from mechanical engineering, and I think that the main sponsor of this event, NSF, but not the IEEE electrical engineering community, wrote a proposal. But this conference, American Control Conference, is sponsored by American Automatic Control Council, which is for which I think many professional technical society belongs. Of course, IEEE electrical engineering, but ASME mechanical engineering, civil engineering, chemical engineering, and so forth. Altogether, 8 technical societies are sponsoring this American Control Conference, and I'm very pleased that we can have this workshop as a part of or in conjunction with the American Control Conference. So again, welcome, and I'm very pleased to be a part of it.
she has done with her students. So, Paris, you can be here, but please, those, Anna was supposed to be here, Fahmida, and Ronald.
So I think there were no questions, or not many opportunities for questions for the last two sessions, but also maybe this is a chance to try to sum up some of the things for the whole day. And so if there are questions of that type as well, maybe they're appropriate as well. So why don't we begin, please?
Can I ask Todd to recommend his book?
I'm sure he's willing to do that.
And I also had a question for whoever the speakers are. Like when I'm talking to my students about control.
Why don't you stand up and then people can hear from you.
When I'm talking to my students about control and systems and so forth, and it's an area they might want to go into, is this systems engineering? Is it a different branch of it? Is it computer engineering but with control? Where does it fit into all the schools? Who wants to ask?
Everywhere. I can try. Control is a very interdisciplinary field.
I'm gonna make people stand up. So people, please, or even come up to the microphone because I think
I can speak loud enough.
Okay.
You could